All right. We are live. I think. Why is this? No. What? Why is this here? I don't want this here. Oh no. Hold on just a second. Why are you like this? Window capture. Create new. Lonely screen. Okay, and then I'm just gonna ignore my face for a second. We will get this going. I don't know why this failed me suddenly. Boom. Too big. And we're good. Okay. Cool. All right, people are here. So I would like to see more people in the Discord chat today, mostly because we're starting with one that's very similar to last time, right? So we have this 450, which is kind of extending what we did previously. Is this great? Everything is going wrong at once. So yeah, can some people hop? I have 2 people in there right now. I would like to see maybe more, or at least enough people that we can discuss things a little bit more. Awesome, I see humans. Okay, so for now, I'm just going to use my finger because I need to charge this thing, apparently. Okay, so why is this not working? Everything is going wrong. Yeah, does someone want to talk through some ideas on how they did 450? I need another USB, but I cannot use another USB. Just kidding, I do have another USB on my desktop. I am a genius. Okay. Should be good. Anybody is welcome to hop in on that. I see some typing. Ah, Ricky. We have to do the subgroup lattice in B. So yeah, the first part is computation, so yeah, feel free. So what generates it? Humans. Okay, yes, I agree. So who wants to talk about this subgroup lattice thing? Mm-hmm. Yep, tops the whole group. Mm-hmm. So you're saying it looks like this. Is this what you're saying? Or where is 4? I think there's probably, yeah, I can draw this in a better way. No. I think this looks better, right? There we go. That looks nicer. Yeah, so Clark made a point, yeah, would it not be similar to the Z18? It is similar to the Z18. Yeah, so the question is, how do we do this? Yeah, it's a good question, Jose. So basically, right, we know that this guy is equal to all of these, right? So we don't really need to consider these anymore. They all give us the whole group. And then the question is, what are the remaining ones? And we only want distinct ones, right? So we don't want to have the repeats show up. So notice we only end up with 6 subgroups total, but there are 12 elements. So we need to see like which ones would be redundant. It still shows me here. It's still working on both of my monitors. Can everyone see me? Okay. Right. So the first thing I do is just like, all right, I'm just going to look at, 2, and remember now, right, I have basically my list of things that are not above. So 4, 6, 8, 10, 9 is before 10. I guess it doesn't really matter. 10, and then of course 0, which is going to be definitely at the bottom, the identity. So these are my 8 guys. And so I know that 2 is 0, 2, 4, 6, 8, 10. And so the question is, which of these are redundant, right? And so this is where we can use our theorem that if they have the same GCD with 12, right? So if GCD of k in 12 is equal to the GCD of 2 in 12, then the thing generated by k is the same as the thing generated by 2. 6 and 4 are in the same order. I have 4 as order 3. I am not saying that. Yeah, sorry. So if you want to be, this guy is technically higher up here. But it's hard for me to draw this, in all honesty. I can just list the orders. Yeah, so this is order 12, obviously. This is order 1, order 2, order 3, order 6, order 4. Yeah. So you were right. Right, we're looking for things with the same GCD. So the GCD of 2 and 12 is obviously 2. And 12 in general is 2 squared times 3, right? So basically, we see that 2 has GCD 2, 4 shares 4, right? So that's not the same. 6 shares 2 and 3, so that's not the same. 8 shares both powers of 2, so it's not the same. 10, though, only has 1 power of 2 and then 5. So these are the same. So 2 is the same as 10. And then you can do a similar thing, right? So I'm just going to look inside there. So obviously 0 is just going to be the trivial, and that's the only one. And then 4, well, this is 0, 4, and 8. But these guys, 4 and 8, have the same GCD, right? Both GCD 4 with 12. And then lastly, you have subgroup generated by 6 there, which has a different GCD again, right? Its GCD is 6, and we get these 4 distinct subgroups. So this gives us this and this, and then we just realize what we have left, and that is 3 and 9. And so my subgroup generated by 3 is 0, 3. Scroll up to the lattice really quick. I can. Yeah, so basically it looks like the Z18 one, just with smaller numbers. Okay, so this is 0, 3, 6, and 9, then you get back. And so, again, we know this has GCD 6. These guys, though, right, like 9 has the 3 squared, but 12 only has 1 3. And so the GCD of 3 and 12 is 3, but that's also the GCD of 9 and 12. And so these guys are the same. And so these would be redundant. So that's why I don't have like 9 listed, that's the same as this guy. I don't have 10 listed, that's the same as this guy. I don't have 8 listed, that's the same as this guy. And obviously I already have my repeats for the generators up here. Does that make sense? Feel good about that? Cool. Okay. So really it's just applying, remember that's theorem like 446 there that we're like applying over and over. They have the same GCD, then they generate the same subgroup. Okay. So now we're getting into some applications of these things that are a little bit more general. So the first one here, this is a corollary to one of our above theorems, so our proof should be pretty quick here. So if G is finite and cyclic of order P, where P is prime, then G has no non-trivial subgroups, no non-trivial proper subgroups. Well, think about it, right? So we know it's cyclic, right? So G is cyclic, and then it's using that same theorem, right? We have this G, or you could even use our corollary to that theorem, which was like specifically this case, when do you have a generator, right? You will also generate the group if the GCD of K and N, so we'll just say the order of G is N here, is 1. Okay, well, sorry, it's order prime, so my N is really this P. Well, that changes things a lot. What has GCD 1 with the prime number? If we're looking at powers, right? We can assume if it's a finite group that all of our powers are between 0 and P minus 1. So what does that tell us? Yeah, any of these, right? All of these, except 0, have GCD K and P is 1. I mean, that's what it means to be prime, right? Like prime, the only thing that divides P would be 1 and P. And so any of these things in between, well, they are not P because they're smaller. And so the biggest thing that they share is 1 as a divisor. And so this means that it's generated by every non-trivial element, right? Thus G is generated by any non-trivial element. And this should look somewhat familiar, right? Because this is exactly kind of the other side of that problem set problem that we had, that if G has no non-trivial proper subgroups, then G must be cyclic. And so here we're saying if G is cyclic, specifically of prime order, then it falls into this case. And it turns out that's an if and only if statement, so this is something we won't prove in here, but just like a fun fact. This is called Cauchy's theorem. So if the order of G is n and some prime divides n, then G has an element of order P. So why am I stating this? Well, the point is, if you have some other cyclic group then, say you have some cyclic group where it's not prime order, then it, has some prime factorization. The point is, you will get a proper non-trivial subgroup, specifically of any of the prime, of any order, a prime divisor of n. Okay, so it's really like an if and only if statement. So if you see no non-trivial proper subgroups, it's cyclic, and it actually must be of prime order. It can't be of, order 9, for instance, because like Z9 has the subgroup generated by 3, which is order 3. So, yeah, kind of a cool fact here. And this is really important in group theory overall, but we won't really, that's more of an Algebra 2 type topic depending on the Algebra 2. The course that you guys would take if you choose that next fall is much more like ring-based and polynomial-based, so you probably wouldn't see this at all. But I'd be happy to talk about it whenever. Okay, so moving on. This should be a quick one. I mean, this is really like a one-line answer. So if there exists exactly one group of order n up to isomorphism, what is this group? Anyone figure this one out? So if I say that, there's exactly one group of order 29, what is this group? Yeah, it's just the cyclic group. So, call it what you want. If you want to call it Rn because we're used to the geometric stuff, you can. At this point now that we have Zn, this is probably the way you would usually see it. So yeah, Zn would be the one. You always have this. It's cyclic of order n. It is a group. So if there's only one, it has to be this one because this definitely exists. Yep. Question? Could I explain the question again? Yeah. So if there exists, so basically, right, we're saying like there is only one group of this order. So basically like your order of G is equal to n, and if you have some other group with the order equal to n, then G and H are isomorphic. So basically like, yes, you could write them in different ways, just like we could write, Zn and Rn, like one's this rotations, one's addition modulo n, but they're the same group, right? They're isomorphic to each other. And so here we're saying like there is only one isomorphism class of groups of this order. So like what must the group be? And just the fact that this does exist means it has to be this one because it's there. Does that make sense? What about S3? Right, so we would not say that there is one group of order 6 because there are two groups of order 6. So that's just one where this would not be a true statement, right? So if, right, it is conditional here. If there exists one group. So for some n, this will not be the case. Yeah. So like 4 also, right? We know that there are 2, the Klein 4 and Z4. So like 4 also would not be true. Z5 though is the only group of order 5, for instance. Do we know what n this is true for? Yeah. It is just primes, right? Yeah, because you always have the finite abelian ones, but we don't have that breakdown yet, so we don't have an easy way to prove that. Actually, well, I guess, yeah, if they're relatively prime to each other, so like ZPQ, Z2 cross Z3 is that. That's true. Is there always a dihedral for any even? There is. Okay. Yeah, I don't think it is either, but yeah, it would have to be an odd order one, right? Where odd order with distinct primes is what you would have to have for that to be true. But we should talk after. Okay. So the next one is a counterexample, maybe. If you think it's true, you would have to prove it. So kind of the next two are related to each other, basically examining orders of products. So, right, if you have 2 elements in your group, is this order m? Yeah. And order of y is n, then like your natural question would be like, is this true? Question mark? I don't know. Right? Can you just multiply their orders? What do we think? Okay. Yeah, so no. So xy is the operation of the group. Mn is just like the number. Because order, we always are just talking about numbers. Yeah. So, right, this is saying xy times xy times xy. This is in G with our multiplication, right? When is this equal to E? And here, if it's order mn, then this would exactly be mn copies of xy here in this product. So that's how this question is phrased. That's what it means. Right, and so I'm seeing a lot of no's and wrongs. I agree. Why? What's your counterexample? Or what's a counterexample? There's probably more than one. Thoughts? Prayers? R4 or an R cubed or order 4? Yeah, that works. So I see R, they're both generators, but this is E, so the order of R times R cubed is 1. There are probably many others that you could have had. I thought of like D3, right? The order of R is 3, the order of S is 2, the order of RS is also 2. It's still a reflection, right? And so that's definitely not 6. This is definitely not 16. V4, product of 2 reflections, is still a reflection there, right? Like your VH and VH. Z12, yeah. So lots of examples. Good. Right, because they're, well, that would be addition, right? So that one actually I think works. So Z12, order of 3 is 4. Okay, yeah, in the order, so 24, and then the product is order 6. or sorry, order 12, yeah, and 12 is not 24. Cool, yeah, that works as well. Okay, so the next two, I'm just going to state. We're not going to prove these right now. Like I said in, I can't remember if that was the email or just the assignment, but I think it was just on this assignment. I kind of said that this starts going a little bit more into like knowledge of LCDs and GCMs and how to manipulate relatively prime things you would normally see in like an intro to proofs or a number theory class. And so I am probably going to write them as problem set problems where I kind of step you through it because we just don't have enough familiarity with this style of stuff right now for me to really feel comfortable asking you to just like prove this without much guidance. But basically what we're going to look at here are finite abelian groups, and we'll come back to this toward the end of class as well. Finite abelian groups, or more generally finitely generated abelian groups, have very, very nice structure. They kind of break down into cyclic pieces in a way, and that's like a big structure theorem that's really, really important in group theory. We're not quite ready for that yet, but we can at least say a few things about finite abelian groups right now. So this is the case where we actually get a yes, an affirmative answer to this question. So let x have order m, y have order n, and specifically such that the GCD of these orders is 1. Then in this special case, the order of the product actually is the product of the orders. So this is a very special case, but it is true sometimes. Okay. All right. And then the one that's more important for going forward, and the last proof that I assigned, is the following one. So again, G is going to be finite abelian. Let N be the maximum order of an element in G, of any element in G. Right, so maybe G has elements, well, clearly it has the identity that's order 1, it maybe has some elements of order like 5, and then 10, and then, it has this one element that's ordered 20 or something, and that's the biggest one. Your N would be 20 there, okay? So we don't know if G is cyclic, so it may not generate the whole group, but it has some element that has a highest order, right? Because it's finite, there has to be a maximum. Okay, then for any G in G, the order of G divides N. Right, so if I have any other element of my group, its order will divide this maximal order of an element. Okay, so that proof is actually, it's not very trivial, but for now, we're just going to take it as true and use it to prove the following statement. So this is kind of a structure theorem about cyclic groups a little bit. So if G is finite abelian and has at most one subgroup of any order, then G is cyclic. Okay, so think back up above. Let's scan way back to where we started. So look at this. Right, so we have a cyclic group. So now this is kind of the converse, right? We're saying like if there's a cyclic group, is there only one thing of every order? But this is just kind of an example for some intuition here. Note that Z12, definitely a cyclic group, but also a finite abelian group. And if you started drawing its subgroup lattice without really knowing that it's cyclic at this point, and you ended up with like 1 order 12, 4, 6, 3, 2, 1, right? All of these subgroups have distinct orders. And it turns out that this C12 is cyclic. So obviously, we can't prove by example here, but this is kind of what's going on. And essentially the idea here seems to boil down to if I had other subgroups of the same order, well, then they had like the same GCD, and so they generated the same group, right? That's kind of what made this happen. So that's more in line with the proof of the following theorem, which is kind of, the converse of this. But it's still useful in terms of gaining intuition for like why this should be true and what's going on. Okay, so let's prove it. So 455 is going to be a useful tool, right? So I gave you a hint in the book, right? So the starting point is going to be to use this hint, right? So let n be the maximal order, like it's after this 455 for a reason. Among all elements of G, of big G. And since it is an order that exists, there has to be some element that has it. And suppose, the order of this little g is equal to n. Then my claim is that this is my cyclic generator, right? So basically my maximal order element, I'm saying, has to be the whole group. Okay, so my suggestion to you was to use contradiction, right? So we'll try contradiction. And then what is the contradiction that we want, right? So this is where we have to go back and think, what did we assume? So one, we know it's finite abelian. And so this is where, right, this uses finite abelian and 455, right? Because 455 relies upon your group being finite and abelian to have some, if we want to end up doing this division, I guess right now this doesn't use 455, but kind of sets us up to use 455. Maybe I'll say that. Sets us up. Okay. And then the other thing is it has at most one subgroup of any order. So if we're going to contradict something, it seems like we're going to be using 455 to get a contradiction that says we have more than one subgroup of some order. So that's kind of my goal here. Goal, suppose G is not generated by this, use 455 to find two subgroups of the same order. And get a contradiction. Okay? Does the setup make sense? Like where we're at now and like where it seems like we should go? Are there any questions? Right. Yeah, I think you're understanding it wrong. I think so. Ricky mentioned that. Okay, there's a subgroup. The trivial subgroup is always order 1. Then you have like the subgroup generated by G. And I think you're saying if this is true, then it would have like two subgroups of like the biggest order, the order of the group. But remember, like if they're equal, they're not distinct. So when I say at most one subgroup of any order, I mean I'm really saying at most one distinct subgroup, because I would not list equal subgroups as different things. So it's really the fact that they are distinct that is important there. Does that clear it up? Right, exactly. Yeah, so if you have more than one generator, then, well, they just generate the same subgroup, so that's fine. Okay. So, well, let's get after it. So we're assuming here that G is not generated by little g. Well, this means there has to be some element that is not a power of G, right? So since G is not equal to this, there exists some, call it whatever you want, say H in G such that H is, I guess I could say not equal to a power, but I'll just say it is not in this subgroup. Okay. So, what do we want to show? Essentially, I should be able to know something about the order of H, right? So by 455, the order of H, call it K, must divide in, which is the order of G. Right? Just because any element, its order must divide this maximal order, because we're inside a finite abelian group. Okay. So this means n is, k times, say, q, the quotient for some q and z. Okay, and we know now that we have this guy, I just want its order, right? This is another definition of order, so we just know that the subgroup generated by it must have order k, and it's not inside the subgroup generated by G. Right, because H itself is not in the subgroup generated by G. So what I'm going to ask you is, can we find some subgroup of the subgroup generated by G of order K? Because this would be a contradiction, right? We would have one subgroup of the subgroup generated by G and then one other subgroup that's not in there, both of the same order. This would give us a contradiction. So this is the key question. Can we find this? And so, can you find this? Can you tell me? So it's a subgroup of a cyclic group, right? So it's got to be cyclic. So can you tell me what power of G must generate this subgroup? So you want to have an idea? Close. So let's look at that for a second. So if I have G to the K, what is its order? So remember, we have 445, right, that tells us how to find the order of things. So this would be in, because it's inside the order of, it's inside the subgroup generated by G, which is order n, divided by the GCD of K and n. And so that's going to be n over K, which is Q. Yeah, it's going to be the Qth power. Basically the same reason, right? It was going to be one of those, essentially. So yes, it's the subgroup generated by G to the Q. So, right, basically, we know all the subgroups have to look like this because G is, the subgroup generated by G is cyclic. All subgroups of cyclic are cyclic. And we know the order. So, I guess it's easier to just write that. So the order of G to the Q is equal to n over the GCD of Q and n. But Q divides n. So that is Q itself. And this is K, because n is K times Q. So we have order of this equals k and the order of g to the q, its subgroup, and these are not the same, right? These are distinct. This contradicts our assumption. And thus, G is generated by little g. All right, so that was not an easy little proof. So, questions? What was our assumption? That there was at most one subgroup of any order, and we have two of the same order. Right. At most one subgroup of any order. Oh boy. I see typing. Okay. Maybe I'll start writing the next thing, and okay, there we go. Could you just prove the contrapositive? If G is not cyclic, then it must have at least two distinct subgroups. Thus, if G has less than two subgroups. No, so it's about subgroups of a single order, right? So it's not just that it only has like one subgroup, right? It could have a trillion subgroups as long as all trillion of them have different orders. So you would have to show that a non-cyclic group has two distinct subgroups of the same order, which would be a little harder than that. No problem. Okay, so the last thing I want to talk about then is 457, and this is basically the converse, right? So if G is finite and cyclic, then G has at most one subgroup of any order. So we know right to left is true. The question is left to right here now true? So it is, and basically the way you want to think of this, right, is what are the possibilities here, right? So can we use any theorem? So this is where I went back up above, right, and looked at like that Z12 example. We saw that like the subgroup generated by 2 is the subgroup generated by 10 because the GCD of 2 and 12 is the same as the GCD of 10 and 12. And what that really is using, right, is more generally 446. If, it's an if and only if statement. So it says the subgroup generated by G to the M is equal to the subgroup generated by G to the K if and only if the GCDs are the same. So GCD of M and N is equal to the GCD of K and N. So now, just suppose you have two subgroups of the same order, right? So suppose the order of G to the M, so this is kind of an aside, so we're not saying that they're equal yet, but just suppose you have two elements inside a cyclic group, right? So G is generated by some G, any element is some integer power of G. So we've got something that looks like this. Well, we know how to get their order, right? By 445, this means that the order of G to the M is N over the GCD of N and M, but this is equal to the order of G to the K, which is going to be this guy. Well, that means these must be equal, right? So we know the GCDs are equal. And then by 446, we get that their subgroups are equal. So this is kind of like those uniqueness proofs, right? Like uniqueness of the identity or uniqueness of an inverse. Just assume you have two guys that satisfy this. They're both subgroups. Are they the same? And we directly prove that they are. You could say it in terms of contradiction, but you never actually need to assume that they're equal. Or that they're distinct. So yeah, you basically just assume they have the same order, you get the same GCD, thus they generate the same group, and so you only have one of each order. Okay. All right, so we are pretty much out of time. So let me know if you have any quick questions here, and otherwise, next time we will actually start symmetric groups. So we'll kind of finish up just like a couple of very brief questions on cyclic groups, and then we've already talked so much about dihedral groups that we're going to kind of skip that section. It's very brief because we have discussed it enough, and then we're actually just going to dig into symmetric groups more generally. Okay. Any questions on anything? I'll grade your test this weekend and try to get those back by Monday, by the way. All right. Fair enough. Well, I'll be in Discord for a few minutes if you have any questions. Otherwise, have a delightful weekend.